Hello, today we're going to be talking about percent composition and doing a quick introduction into how this works and what it is. Percent composition refers to the percent by mass of each element in a compound. It can also be each component in a mixture, but we are going to start by focusing on each element in a compound. We're looking at the relative amounts of each element in a compound. The way that we do this is we take the mass of an element divided by the total mass of the compound, and we multiply it times 100. Now, in this case, you'll hear me say a lot, especially in other videos as well, part divided by whole times 100. We do a lot of things like this where we take a part of something, divide it by the whole, and times it by 100. Now, I'd like to point out here, this is percentage by mass, not by number of atoms. So if we have something like CO2, if we were talking about percentage by number of atoms, it would be 33% of the atoms are carbon and 66% of the atoms are oxygen. But that is not the percent composition. The percent composition would depend on the mass. It's going to be a little bit less than that for carbon because carbon's atoms weigh less than oxygen, so the mass is a bit different. Now we're going to do a few examples today to kind of show how to calculate percent composition as well as how we would calculate the empirical formula from the percent composition. So what we're going to do first is we are going to start with looking at finding the percent composition of potassium cyanide. In order to do this, we need to first figure out the formula. Now we've done a little bit of naming so far, and with potassium cyanide, potassium is going to be K, and we know that potassium has a 1+ charge. Cyanide is a polyatomic ion that is Cn, and that has a charge of 1-. Since those are the same charge, we know that this is KCN. That's what we're going to be doing our percent composition. We are going to make an assumption here. We're going to assume 1 mole. Now, the reason that we're assuming 1 mole is it's just going to make these calculations a little bit easier, and we're just going to be dealing with grams. Now, we're going to need to figure out the full total mass of this compound in 1 mole. In order to do that, we're going to add up our potassium, our carbon, and our nitrogen. Now, due to space, I didn't put the periodic table up here, but I'm going to write these up right now. So potassium is 39.098 grams per mole. Carbon is 12.011 grams per mole. And nitrogen is 14.007 grams per mole. Now, if we want to add all of those up together, there is just one of each. So we're going to take 39.098 plus 12.011 plus 14.007. In this case, we get 65.116 grams per mole. Now, in this case, we are assuming 1 mole. So if we're assuming 1 mole, then the mass of 1 mole of KCN is 65.116 grams. Now, let's go forward and we are going to do the percent potassium, we're going to do the percent carbon, and we're going to do the percent nitrogen in this potassium cyanide. To do this, again, it's going to be part divided by whole, or essentially the element divided by the whole. The whole in 1 mole is 65.116 grams. We're assuming 1 mole, so it's 65.116 grams. Now we want, let me get my laser pointer, we want the potassium first. So we are going to do, there we go, 39.098 grams. Because again, 1 mole of potassium is 39.098 grams. Then we're going to times this by 100. We're timesing it by 100 to make this a fraction. So to calculate this, we would take 39.098 divided by 65.116. then times it by 100. We have, in this case, 5 significant figures. So we're going to go out to 5 significant figures for this one, and we would get 60.044%. For potassium cyanide, 60.044% of it by mass is potassium. We're going to do the same thing for carbon. The number on the bottom stays the same because this is the mass of the potassium cyanide. But on top, we need to now change this so that it's the mass of 1 mole of carbon. Now, just like above, we divided grams by grams, so these cancel out. The grams cancel out again. And to calculate this, we're going to take 12.011 divided by 65.116. Times it by 100, and just like before, we have 5 sig figs, so we are going to go 18.446%. One last one here, we're going to do nitrogen, and we are going to do 65.116 grams on the bottom, and for nitrogen on the top, we're going to do 14.007 grams. And then we're going to multiply by 100. Our grams cancel out, and in order to do this, we're going to do 14.007 divided by 65.116, times it by 100, and we get 21.511%. These are percentages by mass of the 3 elements for potassium cyanide. As a quick check, you should always add all, in this case we have 3, but you should add all 2, 3, 4, however many you have up together and make sure that they add up to roughly 100%. Now, because of rounding, they could be a little bit over 100. In this case, this one's 100.001, but that is close enough. It is just because of how the rounding was. So, for potassium cyanide by mass, 60.044% of it is potassium, 18.446% of it is carbon, and 21.511% of it is nitrogen. This is going to be our final answer right here. Now we can go the other way. What if we are given the percentages and we want to find the empirical formula? Now in this case, same thing as before, just to keep the slide a little bit cleaner and not have a huge periodic table here, I am going to put the molar masses of each of the elements here. So for potassium, just like before, we get 39.098 grams per mole. Now, we also have Mn here, and so that's going to be manganese. And for manganese, it's going to be 54.938 grams per mole. And then for oxygen, we have 15.999 grams per mole. Now, we are given the percentages. We are told percent by mass, 25% potassium, 35% manganese, and 40% oxygen. We are going to make an assumption, but it's going to be a little bit different than the previous one. We are going to assume 100 grams. The reason that we're making this assumption is it is really easy for us to go from 25% potassium and 100 grams to grams. 25% of 100 grams is 25 grams. So we are going to do potassium, manganese, and oxygen. And we know for potassium that we have 25.0%. For manganese, we have 35.0%. And for oxygen, we have 40.0%. Now, as I said before, we can easily switch these into grams if we assume 100 grams. And instead, we have 25 grams, 35 grams, 40 grams. When we're talking about an empirical formula, we know that that is the lowest whole number ratio, mole ratio for the elements. So we need to get these into moles since that is a mole ratio that we're looking for. What we're going to do is we are going to convert this amount of grams of potassium, this amount of grams of manganese, and this amount of grams of oxygen into moles. I like to put my numbers over 1 so that I can see that grams of potassium is in the numerator of that fraction. I'm going to take my molar mass from up there, which is 39.098 grams, and it's going to be 1 mole on the top. My grams of potassium cancel out, and when we're calculating this, we're going to take 25 divided by that 39.098. In this case, we have 3 sig figs because the 25.0 has 3, so we get 0.639 moles. We're going to do this again for the manganese. In this case, it's going to be 1 mole on top again, but our manganese is 54.938 grams. To do this math, we're going to take 35.0 divided by 54.938, and again, 3 sig figs, so we are going to get 0.637 moles. Up next, we have oxygen. In this case, we're going to convert it to moles as well, and we're going to have 1 mole over 15.999 grams. We're going to take 40.0 divided by 15.999 grams, and we're going to get 3 sig figs again, so 2.50 moles. Now we can't write K 0.639, Mn 0.637, O 2.5. Those aren't whole numbers, and we can't put those as our subscripts for an empirical formula. So what we're going to do is we are going to divide these by the smallest number of moles. In this case, that's this 0.637 right here. So we are going to divide this by 0.637. We're going to divide this by 0.637. And we're going to divide this by 0.637. And when we divide these, what we're doing is we're putting it in a ratio. We're putting it in terms of manganese being 1. And that's why this works, is we are putting this so that everything is really in relation to manganese being 1. Now, for 0.639 divided by 0.637, it is about 1.003. However, we are just going to say that this is roughly equal to 1. It's very close to 1. For the 2.5 divided by 0.637, what we get is about 3.92. We're going to say that that is close enough to 4 here. Now we have all of these in relation to manganese being 1. For our formula, we get K1, Mn1O4, and then remember we turn any 1s as a subscript as to implied, and so we get KMnO4. This is the empirical formula from a sample containing 25% potassium, 35% manganese, and 40% oxygen. We're going to do one last one here, and this is a little bit simpler than the other one. This just has 2 elements. We have silicon and we have nitrogen. And so just like before, just to keep it a little bit clean, I am going to put the molar masses up here. Silicon is 28.086 grams per mole. And nitrogen is 14.007 grams per mole. Just like before, we're going to make that assumption where we're going to assume 100 grams. We're going to have silicon, and we are going to have nitrogen. In this case, 60% of silicon means that we have 60.0 grams of silicon. 40.0% of nitrogen means we have 40.0 grams of nitrogen. Very similar steps as last time. We are going to convert these both into moles. For silicon, we have 28.086 grams, and then 1 mole on top because we want those grams to cancel out. In this case, we would take 60 divided by 28.086, and we get, with 3 sig figs, 2.14 moles. We're going to do the same thing with nitrogen. We're going to put 1 mole on top, 14.007 grams on the bottom. Our grams cancel out, and we take 40 divided by 14.007. In this case, we get 2.86 moles. Now again, we can't put SI 2.14 and 2.86. They have to be whole numbers. So we are going to divide these both by that 2.14 moles. What we're doing is we are putting these in a ratio so that silicon is, it's everything in relation to silicon being 1. When we take 2.86 divided by 2.14, what we're going to get is 1.34. Now, in this case, that is not close to a whole number. But what we could do is we could times it by 3. If we times this by 3, we're going to get pretty much 4. But if we times that bottom one by 3, we need to multiply the top by 3. If we get a number that's close to 1.33, we'll multiply by 3. If we get something close to 1.5, we'd multiply by 2. 1.25, we'd multiply by 4. We're trying to multiply both of them to get them to both be whole numbers. In this case, this empirical formula is a little bit different. This one's SI3 N4. If you have any questions, you can comment below. Otherwise, I hope you enjoyed learning about percent composition.